Alright, in this video we are going to learn about some introduction on the linear regression, both simple and multiple linear regression, and how to use R to calculate those. Okay, so to study the relationship between two variables, we collect data and construct a scatter plot and determine the types of relationship the variables have. Also, we evaluate the correlation coefficient R. Okay, that is the correlation coefficient. This is the same correlation coefficient you calculated in the elementary statistics class. Okay, and test the hypothesis. If one of the variable depends on another, then such dependent relationship is called regression. Okay, the term simple regression is used if there is only one independent variables. Okay, example, blood pressure and age. A person's blood pressure depends on age but not vice versa. The blood pressure may depend on other factors too, but age is one of the independent variable. Okay, so if the blood pressure depends on other variables, for example, let's say blood pressure is Y, that is dependent variable. Okay, the independent variable can be so one of the independent variable can be blood pressure, the age, right? So the one of the independent variable can be age, the other independent variable can be other things, right? For example, so other factors can be the cholesterol, right? So the cholesterol can be another independent variable. Okay, so but the blood pressure can depends on the cholesterol level, age, and so on, right? So it can depend on a single variable, single independent variable, that is called simple linear regression. If it depends on many independent variables, then it is called the multiple linear regression or multiple regression. Okay, the line of the best fit, also called regression line, is a line that goes through most of the data points. So this is the regression line, these are the data points, right? Or close to them. In other words, the regression line is one with sum of the square of the error is minimum. So what do you mean by the error? So this is the line that you estimated from the data, and these are the data. Okay, see, your line is that, but the data is here. This line does not pass through this data, so this is the error or the difference, right? The deviation. So that is D, and that is another deviation, that is another error, that is another error, that is another error. So there are so many such errors, right? If you square the difference and add them, that is called the sum of the square of the error, right? And that is the minimum. So because you can draw so many such lines, right, that go through close to the points, but we will pick the one that has the smallest sum of the square error only. That is called the regression line. So regression lines are very useful to see the trend and make prediction on the basis of the data. So what is the simple linear regression line? Let's talk about the simple linear regression line first. So y hat equals to a plus bx. So where y hat is the predicted value that you will be predicting from this line, a is given by this formula, okay, and plus b is given by this formula. This b is called regression coefficient, okay, and x is the independent variable. So x is the independent variable, okay. So the regression coefficient b is the basically sample regression coefficient here. For the population regression coefficient, you write y equals to alpha plus beta x. So alpha is a constant or the y-intercept, right? And beta is the slope here, or basically the regression coefficient, okay? So is the y-intercept of the regression line from sample. It is also calculated using a equals to y bar minus bx bar. To find out a, you can use this formula too. Xi are the values of the independent variables, and yi are the corresponding values of the dependent variable. So this is how you do if you want to do by hand, because you know the data will be given like x and y, right? So what you need to do is you need to find out x times y. So x times y. Also you need to find out x square, right? And then another column will be y square, and then you find out Just write down those values of x, write down those values of y. So so these are basically xi times yi is, this is x, the first value of y. So you multiply this with that, write down here, right? And find out x square, another column will be y square, and so on. Okay. So in that way, you plug in here after you find out all those values, and then find out a and b, and then you plug in a plus bx, which is the simple linear regression line. Okay. So if xi, yi are the corresponding values of the dependent variable, the population parameter for these statistics. So this is the sample the equation for the sample, right? If you want to do the population, for population, it will be y equals to alpha plus beta x. This is for the population. Okay. So alpha is the y-intercept and beta is the regression coefficient in the population. Okay. Usually we round these values to 3 decimal places. If the slope of the regression equation is positive, that is b is positive here, we can interpret that for every 1 unit increase in x, we will get b unit increase in the variable y. If b is negative, then it will be decrease, right? The number b is called marginal change. So b is the regression coefficient from the sample. So b is also called the marginal change. Okay. Let us do an example here. So the number of murders and robberies per 100,000 population for a random selection of states are shown. Find the equation of the regression line. So you have to follow those steps, right? You need to make a table, write down x, write down y, find out x times y, and then x squared, and then y squared, and plug into this formula. Okay. If you do that, you will find out the value of a and b. Next, what you do, you write y hat equals to a plus bx. Just write down that value and that value here, right? So a will go here, and then plus b times x go here. And after you get that, you take x equals 4.5 and find the values. Okay, I have done that in R. Let me show you that. So I copied the data here, murders and robberies. So this per mf row, see 1 by 1 means sometimes if you want to see more than one figure here, like 2 figures on the top and 2 figures on the bottom, you write 2 by 2. But 1 by 1 means I want to see only one figure there. Okay. So what I'm going to do now here is I want to see the scatter plot. Scatter plot means this is like x, this is like y. Okay. And then what I'm going to do is I'm going to plot x comma y. Okay. So 2.4, 25.3, 2.7, 14.3, and so on. Let us see how does it look like. Let me run x, let me run y, and that is thus it will give you just only one graph. So when I do the plot, you see that these are the values of the data points x comma y. Okay, so here this is called the scatter plot. From the scatter plot you can see that the line, you can see that it is almost linear, right? Because you can draw a line from the middle. We will draw the line later, but you can imagine the line goes from the middle, so it looks like the line is increasing, right? So the slope is positive if the line is increasing, right? If the data is increasing for the increasing values of x, if the y values are increasing, then you expect the value of the b is positive. Okay, so let us do that. So let me find out the values of a plus bx. Okay, so here, so a is the intercept, okay, and then b is the slope. Okay, so the intercept is given as intercept. Okay, that is the intercept a, and then 25.33 is the b. So how would you write this one then? So basically what you have is a is negative 13.15, and then b is basically 25.33. so this is negative 13.15, right? And this is 25.33. okay, so how do you write that? Is negative 13.15 plus 25.33x. okay, what it says is you replace x by 4.5. if you do that, you will get negative 13.15 plus 25.33 times 4.5. you see that? So if you do that, you will get let me see what you get there. So if you do that, you will get, let me show you that x equals to 4.5, y is a plus b times x, right? If I do that, I will get 100.835. You see that for x equals to 4.5, you expect the value somewhere here, right? Because the line will go from the middle. So you expect the value somewhere here, which is 100.835. Let's write down that. That will be positive 100.835. So this is how you find out the value of A and B. Okay, there are some notes. If you are using calculator, you need to turn the diagnostic on from the diagnostic from catalog by second and then 0 and then scroll down to diagnostic 1. But we don't use calculator, we just use the R, right? So what is the syntax for R? You just see that you write x equals to the x data, y equals to the y data. If you want to see the scatter plot, just do plot and then x, y, right? That's what you do. And if you want to find out the values of A and B, what you do is linear model. You write down first y, okay, and then do x. That's what you do. Linear model, y, and then that wiggle sign, and then the x. You see that? Let me show you that again. The y is the rivalries and the x is the model. There is the wiggle sign there. Y and then x. Okay. So this is how we find out the regression coefficient beta and then or b and then a. Okay. So to compute A, B, C, and R values, you use this is just what you did in the basic elementary statistics class, how to use calculator. Okay, let's talk about the outliers and the residuals. Outliers and the influential point. Outliers is a point that is further away from other points. Influential points are those that affect the graph of the regression line. Okay, which means without those points, the regression line is far better. Goes through most of the points or close to those points. So we will talk about how do I find out the influential point and outliers later. Okay, there is a way to find out in R for that. Next term is residuals and least square property. The concept of the regression line is the one that best fits the data, but this is not possible. For a fixed value of x, the distance of the point from the line is called residuals. Okay, you see that on this graph. So for this point, this is the line you get, right? But this is the data. So this is the residuals. This is another residuals. This is another residuals. Another residuals. So basically, the distance from the point to the line is basically the residuals, right? The distance from the point from the line is called the residuals. We denote the sample residuals by E sub I. Basically error, right? So it will be E1 is the difference, the distance from the point to the line. E2 will be first point to the line. E2 will be distance from the second point to the line, and so on. So residual plot is to find out the residual EI values. We use EI equals to YI is the data minus the value for value of y from the line. Okay, that's how you find out the error or the residuals, where yi denotes the observed sample values, that is the data, and yi hat is the estimated value using the regression equation. Then we plot x and ei. So we plot x versus ei. Okay, for the population, that ei is denoted by epsilon I. Okay, for the population. All right, let us see this example. Residuals and the plots. So there is a data x and y, circumference and the height. So 1.8 is 21, 1.9 33.5, 1.8 that. So there is some data, circumference and height. So what we are doing here is this is like x and this is like y. Okay, now when you do that, circumference is x and height is y. So what we are doing here is we are finding out the line of regression or the regression line, that will be y equals to a plus bx. You can use R or you can use calculator, whatever you use, you will find out this line. Okay, so this is x data, this is y data. Now this is the predicted data. How do I find the predicted data? What I do is I plug in x equals to 1.8 here and I got that value, x equals to 1.9 here. So these are basically the predicted value from the given from the equation you obtained. Okay, and what is the residuals? Residuals is your y value, the data y minus the predicted y. Okay, so the data y minus the predicted y, data y minus the predicted y values. Okay, so this is basically the residuals. So if you do the scatter plot like x versus y, this is the scatter plot for height versus the circumference. But this is the residual plot. What you do is you plot x versus the residual values, x versus the error. You see that? You see almost the similar patterns. You see that for the lower values around 2, the data are close to the line, right? Predicted line. Similarly here, close to 2, the data are close to the horizontal line here, right? So, and then after you go around 5 or 6, the data are far away from the predicted line. Similarly here, the data are far away from the horizontal line. Okay, so you will see the similar nature, but in the residual plot you see it better, because in the residual plot you draw a horizontal line and you see the data. It is easier to see. Okay, from the residual plot you can actually expect, or you can see most of the important feature. Okay. We can better estimate, better see whether the data are around the horizontal line or not. Okay, if the data are approximately equally distributed above and below the horizontal line, then the linear regression model is good model. Sometimes the scatter plot shows linear pattern, but residual plot does not show a linear relationship. In this case, linear regression model may not be the best model. Although you see the scatter plot a linear relationship, for example, look at this one. It looks like it is linear, right? But when you find out the residual plot for this one, you don't see the linear relationship. Okay, so it is better seen in the in the residual plot. It is better seen. Okay, suppose this is figure A, this is figure B, this is figure C, this is figure D. So can you guess which graph, which of these 4 graphs is the residual plot for scatter plot 1? For the scatter plot 1, okay, so you will see that for the smaller values, the data are very close to the line. For the bigger values, the data are more scattered, right? Which one has that? I think it has that one, right? A. Because see, for the smaller values of x, the data are close, but for the bigger values, the data are more scattered, right? This will be A. And the second one is, see, it looks like everywhere the data are equally scattered. You see that? Everywhere the data are equally scattered, but little more scattered. Looks like this is B, right? Because you see that, and this one looks like C. This one looks like D. Why is that? Because it is decreasing, but see, all the data are very close to the fitted line or the regression line, and here the data are very close to the horizontal line, right? But here you see that the data are below for the smaller values and the bigger values, and the data are above for the middle values, right? You can see the same type of pattern here. So it will be B, C, D, A. So basically you can see the better non-linearity in the residual plot than in the scatter plot. That's why when we do the statistical analysis, we check the residual plot, okay, not the scatter plot. What are the prediction interval? Do you remember that y equals to a plus bx, y hat equals to a plus bx gives you the best fit line or the regression line? But when you say what are the values of y hat, predicted value of y hat, if x is some value like say 4.5, then you assign a value of 100 point something. That's what we got in the example, right? But that may not be 100% true, because we are not 100% sure that it will be 100 point something, right? So what you do is you usually assign an interval. For x equals to 4.5, you say the predicted value will be somewhere between 98 and 102. That is basically the prediction interval, okay? So we learn on how to predict a value of y using a linear regression when a value of x is given. But it sounds better if we say that for a given x, y values, predicted values lie between 2 values, right? This range of the value is called the prediction interval. Okay, Usually, we use statistical software to find out these results. The following formula is used to find out 1 minus alpha percent prediction interval for the given value of x sub 0. So y hat minus me, margin of error, is less than y hat or y. This y is for the population, okay? So this is for population. So let us not write y hat. And then y hat plus the margin of error, where the margin of error is given by this is the critical value for the t with n minus 2 degrees of freedom, and then se times that, where se is given by that. So we will do all these things in R. I'll show you how to do that, okay? So if you want to do it by hand, this is how you do it. Okay, now the next thing you do is, okay, so whenever you find out say y hat equals to a plus bx, you can say that if b is positive, then the linear relationship is increasing, right? If b is negative, it will be decreasing, and so on, right? If b is 0, then we would say that y does not depend on x, okay? But this is only for the sample though. So how do I test the hypothesis based on this? How do I test the hypothesis for the population? That is y equals to alpha plus beta x, right? This is y hat for the sample, y is for the population. So based on beta, if beta is non-zero, meaning y depend on x, right? So can we conclude that in the population y depend on x or no? To do that, we do the hypothesis testing again. So I will talk about the how to do by hand here, but I will show you how to do by using the R, okay? In the regression line, y hat equals to a plus bx, the slope b expresses the straight line dependence of y on x in the sample. But the relationship between x and y in the sample, that is b not equals to 0, does not necessarily mean that there is a dependence in the population, okay? It is possible that even though y does not depend on x linearly in the population, a small sample can show a linear dependence of y on x. Just in the hypothesis testing, we want to assess how likely it is to obtain a sample with non-zero slope from a population with 0 slope. Thus, our null and alternative hypothesis is H0 is beta equals to 0, meaning there is no linear relationship, versus H1 is beta not equals to 0, meaning there is a linear relationship between x and y. To find the test statistic, we need the following values. Total sum of square is y minus y bar. So what you get, because you will have x and then y, right? And then, so what you do, you find out y bar, okay? And then you find out y minus y bar square, okay? So you can do y minus y bar. So y minus whatever that you get, and then square that, okay? And another y value minus y bar, and then square that, and so on. And there is another alternative formula for that. It's just simplification of that. If you simplify this, you will get that summation yi square minus summation yi over n square, okay? Degrees of freedom is n minus 1. Similarly, regression SS is y hat, the predicted y value minus the y bar value, square sum of that. Or if you want to use the alternative formula, degrees of freedom is k, okay? And residual SS is, so summation yi minus yi hat, meaning this is the data minus the predicted one. Or another way of finding this is total SS minus the regression SS, with degrees of freedom is n minus k minus 1. What are n and k? So k is the number of independent variables. So how many independent variables are there? Here we are assuming that x is the only independent variable. So there is k is 1, okay? So also to find out the corresponding mean square ms, we divide SS by degrees of freedom, and the test statistics will be regression ms over the residual ms. So to find out the total ms, how do I find out the total ms? Total ms is SS divided by degrees of freedom. So SS divided by n minus 1 will be the total ms. What is the regression ms? Regression ms will be regression SS divided by the degrees of freedom, right? K. So and so what is the residual ms? So residual ms will be residual SS divided by the n minus k minus 1. This is what it says. We divide SS by degrees of freedom, okay? The test statistics or the F value is regression MS over regression residual MS. Okay, the critical values are obtained by using F table with K and N minus K minus 1 degrees of freedom. So F alpha 1 and then K N minus K minus 1. So the test is always the right tail. That's why we use alpha 1. That is the right tail test, one tail. So if the test statistics fall in the rejection region, then we reject the agent. This is how you use hand by hand. Okay. So let us talk some more thing, and then I will show you how to use R to do this problem. The residual mean square is often denoted by S square Y dot X. Its square root is as yx. Is called the standard error of estimate. Okay, this quantity is an indication of the accuracy with which the fitted regression function predicts the dependence of y on x. What is the coefficient of determination, which is also important thing when we do the analysis? The ratio of regression SS and the total SS is called the coefficient of determination. So regression SS divided by total SS. Okay, how do I find those regression SS and total SS? There is, okay, this is total SS, this is regression SS. If you divide one by the regression by the total SS, then you will get R square. R square is often used as a measure of strength of the straight line relationship. It is sometimes referred to as expressing the goodness of fit of the line, how strongly the data is fitting to the line, okay, to the data as of the precision of the regression. The following data is the wing length of the, this is the example that I'm going to discuss in R. The following data is the wing length of a sample of 13 sparrows of various ages. Find the regression line with alpha equals to 0.05. Test the dependence of wing length in the sparrow's age. Okay, so let us see whether the wing length depend on the age of the sparrow's bird or not. Also find the standard error and the coefficient of determination. So you want to find out the standard error and you want to find out the coefficient of determination R square. Okay, so what is the standard error? Standard error is as yx value. Okay, the freedom, right? Yes. So we will see that in R, but let us see that the regression line you find out from the R, you will find out A plus BX, right? A plus basically BX, right? This is A plus BX. And what is the null hypothesis? Null hypothesis beta equals to 0. Alternative hypothesis is beta not equals to 0. So we find out the test value. So this is how we find out using R. Using the hand. So let me find out this using the R. These are the two data, X and Y data points. So we want to see whether the length of the wings depend on the age or not. These are the data values. Okay, for the 3 years old it is 1.4, for the 4 years old it is 1.5, and so on. So what I'm trying to do here is I am trying to plot length versus the age. Okay, I'm just plotting this in basically in a table, but no worries. But for now we will do that later, but for now let's plot the length versus the age. You see that this is almost a linear relationship. You see that this is almost the linear relationship. And then so what is basically the y, A and B. So you see that A is 0.7131 and then BX, right? B is 0.2702. You see that what is our A is 0.71. There was 713, but here I got 715. So this may be because of the problem on how many decimal places I pick, right? But they are almost the same, 0.27, 0.71, right? So that's what we got, 0.27 and 0.71, right? Okay, now what you want to do is you want to test the hypothesis for beta. Okay, when you test the hypothesis for beta, that is the summary of model 1, 2. Model 1, 2 is the name that I gave for the linear model. So here you see that LM is the linear model, and then you do length, that is the Y, the dependent variable, and then wiggle sign, and then independent variable. That's what you do, right? We did that already here. LM is the linear model. the dependent variable and then independent variable. So y first and then x. That's what you do. And then when I did the summary, what I found here is it also gives you the summary of the residuals. What is the smallest residual value, what is the q1, q2 and q3, and the maximum residual value. But the important thing here is you see that this is the A, this is the B. Okay, so this is for B, right? The testing for B, we got that P is less than alpha. This is the P value which is less than alpha. So it is significant, meaning that we reject the null hypothesis, right? This null hypothesis should be rejected, meaning in the population there is a linear relationship, because beta not equals to 0 means there is a linear relationship. Okay, let us go back. What else do we have here is residual standard error is 0.2184. That's what we got, and the degrees of freedom is 11. Multiple r squared, we got the r squared is 0.9733. so residual standard error is basically the square root of the mean square error, right? So you see that residual standard error is that much. And then how do you find out the SYX? SYX is this divided by the degrees of freedom. Okay, so you see that. How did we define the call the standard error estimate? So which is the residual mean square error? This is the residual mean square error, right? And the square root of that is the standard error estimate. Okay, that's what it was asking. So this is what we were finding from here, and we got exactly the same values. You see that residual standard error, okay, and then which is same as the mean square error, right? And then the degrees of freedom is 11, and the multiple r square. So r square value is 0.9733. and adjusted r square is 0.9709. Let's see what we got the r square there. R square is 0.97. You see that we got the same r square values from there. So you do so this indicates the strong linear dependence of the wings length in ages. You can do the above example using the t-test. Actually that r is using the t-test. This method is more useful if you are testing one-tailed test. Also if you are testing this. So what it says is if you are testing for H0 is beta equals to beta 0, because what we just tested is beta equals to 0 versus beta not equals to 0, right? So no linear dependence versus linear dependence. But if you are testing for beta equals to a certain number other than 0 and beta not equals to a certain number other than 0, then in that case t-test method will be more useful instead of the ANOVA method. So what we did is the ANOVA method. We are using the F statistic and then F table and so on. But what we were testing beta equals to 0 versus beta not equals to 0. Okay, but if you are testing for beta equals to beta 0 and beta not equals to beta 0, then you use the t-test method instead of this method. All right. So linear regression model, you just look at this value only for the p value, whether you reject or don't reject the null hypothesis, right? And look at the residual standard error. That's what the question was asking. Also the r square, that's what the question is asking. Both of r square is 0.97, right? Is 401.1 is the value of the F statistic, and the degrees of freedom is 11. So if you look at that, that's what we got the F statistic, right? The F value here is 401.1. So what do you get? So if you want to draw the line between on those that goes close to these points, or the regression line, what should be the regression line? It should be A plus B times X, right? A plus B times X. If you do that, then you will get this line. You see that? That is the AB line, and then model 1, 2. And then color is red, whatever color you choose, and then this is the line width 3 or whatever line width you want to make. Okay, 95% prediction interval. Okay, so the 95% prediction interval for y for all x values. That means because you find out y equals to a plus bx, right? Y hat equals to a plus bx. From that line you plug in x values and find out the 95% confidence interval. So what you get here is, see, so these are the fitted values, okay, and these are the lower and upper lower and upper bound for the 95% confidence interval. Okay, so another thing is confidence interval for the regression coefficient for the beta. What is the confidence interval? 95% confidence interval for the beta is, so you see that for the A's this is B, and then these are the confidence interval for beta. So smaller lower bound, this is the upper bound for the beta. Okay, so do you remember what was our beta value? Our beta value is 0.2702, right? So the 95% confidence interval is 0.2405 and 0.2999. That's what you get. So you can find out the 95% confidence interval for beta as well as for the all y fitted y values in R directly. All right, guys. Okay, so